Hello friends, today we have very interesting topic about the concept and theory of the stress and strain. So stress and strain is very important topic for the structural geology and even in geology because stress is the only factor that develop the so many structures in geology, and these structures are very important to understand the geological structures, orogeny of the area, and yes, obviously, to understand the economical deposits also. So, stress and strain concept is very important. According to Hocken and Fossen, strains can never be observed directly. We have to use the observation of a strain. So, the Hocken and Fossen describe that stress can never be observed directly. To understand the stress distribution in the crust or in rock, we have to observe the strain. But recently, science has developed and we have some methods. So, based on these methods, we can calculate active stress or present stress in the area. We will discuss these methods after the concept of the stress and strain in further slides or upcoming slides. Okay. So first of all, force. In geology, we have two types of force. One is body force and another one is surface force. Body force are those forces those affect the body from outside, inside, and change the volume also. For example, gravity force and magnetic force. Surface forces are those forces those act only on the surface. And these forces, the surface forces generated due to the movement of two blocks over one another. So such type of force is known as surface forces. And stress on a surface is also known as traction. Then stress on a surface. Stress on a surface can be represented by F upon A, means force per unit area. But actually, geology in homogeneous, so stress is always change from place to place. So we can represent the stress here limit del A del to 0 del F upon del A. It means that stress change from place to place. In geology, compressive stress is always considered positive and tensile stress as negative, but in material science, it is reverse. Compressive stress considered as negative and tensile stress considered as positive in material science, but in geology, compressive stress is always positive and tensile stress is always negative. A stress vector perpendicular to a surface is called a normal stress and parallel to the surface is known as the shear stress. So this is the Mohr convention. We can see this is the compressive stress and this is positive, and these are the tensile stress. This is negative. So here we have one force acting on a surface. So parallel to the surface, there are many factors, many vectors of the force. So that vector of the force that acting parallel to the surface, that is known as shear force, and the vector that is acting perpendicular or normal to the surface, that is known as normal stress. Okay, here the angle between the force and the normal is known as the theta. This theta angle is very important when we discuss about the Mohr circle. Okay, so here normal stress can be represented stress cos square theta and shear stress sigma sine 2 theta by 2. Okay, then there are infinite numbers of stress vector, and when we draw the mean vector of each plane on a point like this, an ellipse emerges in 2D. An ellipse emerges in two dimensions. The ellipse is called stress ellipse and the ellipsoid is called the stress ellipsoid. So in stress ellipsoid we can represent the sigma 1, sigma 2 and sigma 3 axis also. This sigma 1 is the principal stress direction axis, sigma 2 intermediate and sigma 3 is the minor stress axis. So here we can see this is the foliated rock, and this foliation represented here, this is the foliation direction. So this is the sigma 1 stress direction, greatest direction. So the foliation orientation is like that. So Why this position direction is like that? Because this is the strain axis, this is the stress axis. So strain axis and stress axis always perpendicular to each other. So here we are applying the force from this direction, that's why we have more and more, or we can say most deformation towards this direction. So this is the minimum stress direction, but when we talk about the strain, this is the principal strain direction. Okay, now this is the um, stress tensor, or we can say this is the stress matrix. So we can represent the stress matrix at every point sigma 1 1 sigma 1 2 by 3 by 3 matrix. So the this whole matrix represent the stress tension. Here sigma 1 sigma 2 and sigma 3 are the principal stress axis, intermediate stress axis, and the minus stress axis. So here if we call this is the mean stress, if we take the mean stress, so mean stress we can represent by the matrix like that. This is the stress tension. So the dioelectric stress is the um, dioelectric stress can be represented by stress tension minus mean stress like that. Okay, so if sigma 1 is equal to sigma 2 and sigma 3, so that means that plane is perfect sphere, there is no shear, or we can say that is the hydrostatic stress. Here this is the Mohr circle. So first of all, Mohr circle is invented by uh, Otto Mohr. Otto Mohr is was the German engineer, and by this German engineer, this Mohr circle was invented. In Mohr circle, suppose that this is a plane. Here, the incidence angle is the theta, and here the incidence angle is the 2 theta. Here the diameter of the Mohr circle is principal stress direction plus minus stress by 2. This is the mean of principal and minor. So if we take the diameter of the Mohr circle, that is principal stress and the minor stress. So we have to plot the Mohr circle here. This 2 theta angle, why this is 2 theta angle, we know by a theorem. A theorem is say that the the angle on a circle will be the double to the angle of the periphery. Here this is the point we want to calculate the shear stress and the normal stress on this axis. In the Mohr circle, the horizontal axis represented by the normal stress and the vertical axis represented by the shear stress. Let's take a diameter sigma 1 plus sigma 3 by 2. This is the diameter. So we draw a circle here. On this circle we have a point P. On this point P we calculate the normal stress as well as the shear stress. So here we apply a force. So the angle, the applying force and this point uh, make an angle that is theta. So this theta angle, if we reflect this on the center, it will be double, because we know by the theorem the angle on the center will be the double to the angle of the periphery. This is the 10th standard theorem. Okay, और we can say केंद्र पर बना कोण परिधि पर बने कोण का दोगुना होता है. Okay, so the distance from the shear axis to the center will be sigma 1 plus sigma 3 by 2, because we have draw this whole circle by the diameter. Okay, the distance from principal stress to the center sigma 1 minus, because this is the sigma 1, so if we want to calculate we have to take the mean from the principal to the minor one, so this will be sigma 1 minus sigma 3 by 2. If we want to calculate this distance from center point to the normal of the this point, so here will be the normal stress for the point of P. So the normal stress will be sigma 1 minus sigma 3 by 2 into cos 2 theta. Similarly, if we want to calculate this distance, or we can say the shear stress, so shear stress will be sigma 1 minus sigma 3 by 2, that will be sin 2 theta. So this is the simple nomenclature of the Mohr circle. If we want to plot the different kinds of stress on Mohr circle, so what will be the representation? And this is the first case for the hydrostatic pressure, means there is sigma 1 is greater than sigma 2 and sigma 2 and sigma 3 is 0. Okay, so here this is the point, or sigma 1 or sigma 3 is equal to P. So this will be the point here. Actually, this is hydrostatic pressure. So hydrostatic press, there is shear stress component is zero. That's why it will represent on the normal stress axis direction, and the matrix will be like this. Then uniaxial compression. In uniaxial compression, sigma 1 is greater than to sigma 2 and sigma 3, and sigma 2 and sigma 3 will be 0. So in uniaxial direction, okay, uniaxial compression, the nomenclature will be at the normal point, and there will be no component of the means. This circle will be represented here. This is the A condition for the uniaxial compression. Sigma 2 and sigma 3 is the 0. Sigma 1 is greater than sigma 2 and sigma 3 and not equal to 0. So this is the uniaxial compression condition, and here uniaxial compression can be represented by the matrix. Means uniaxial compression means only one component is a unit, other all the components will be 0. Then uniaxial tension. In uniaxial tension, sigma 1 sigma 2 will be 0, and sigma 3 will be greater than, or I mean will be less than to the 0. So this is the representation. Here we can see this is this horizontal axis normal stress. So if we move towards the left direction, it will be minus, and if we move on the shear stress axis towards the downside, from the center point, it will be minus. So tension always create in the negative points. So here this is the negative axis, so the Mohr circle will be flowed towards the negative direction, and by the matrix it will be represented by negative marks here. Okay, then axial compression stress, or axial compression or confined compression. In this case, sigma 1 will be greater than sigma 2 and it equal to sigma 3, but sigma 3, this is non-zero condition. So in the on the Mohr circle we can represent such type of condition like this. This is a Mohr circle. Here sigma 1 is the greater than to the sigma 2 and greater than sigma 3, and sigma 2 and sigma 3 is non-zero condition. So this is the axial compressive stress or axial confined compression. So by the matrix A, B and B, because sigma 2 and sigma 3 is equal, that's why we have given the same number here. Then triaxial stress means sigma 1 greater than sigma 2 greater than sigma 3. Here this is sigma 1, then we have sigma 2, then we have sigma 3. So for the stress matrix we have given all the numbers in different A, B and C. Then axial extension in or extensional stress. Axial extension or extensional stress. Sigma 1 is equal to sigma 2 and sigma 2 greater than sigma 3 in the matrix A and B. So sigma 1 and sigma 2 will be at the same point, and sigma 3 is non-zero, that's why it will be here. So we can represent by the Mohr circle like that. Then pure shear stress or pure shear, sigma 1 is equal to minus sigma 3 and sigma 2 is equal to 0. So here we can represent the two circle, that one is towards the positive axis, another one is towards the negative axis, and the common point will be passed through the 0 point. So this is here sigma 2 is 0 for this circle, and for this circle also here sigma 1 is the greater than sigma 3, equivalent to sigma 3. The value of the sigma 3 on both the axes towards negative and positive will be the same for the pure shear stress. And for the matrix A and minus A, and B will be 0 because this is sigma 2 will be 0 here. Then divoitric stress. Divoitric stress can be represented by sigma n, where sigma n is equal to sigma n is equal to, so we can represent that sigma 1 is equal to sigma 1 minus sigma n. This is the mean stress. So we can represent the geometric stress from the stress tension minus mean stress. Then differential stress. Differential stress will be sigma 1 minus sigma 3 because sigma is the principal one and this is the minor one. So differential stress can be represented like that. Then effective stress. Effective stress will be sigma 3 is equal to sigma 3 minus PF. Okay. Then stress measurement. Now these days we can measure the stress, and this stress measurement is very important for the civil structure. Suppose that we are going to we are going to construct the civil structure in the high stress region. Those are tectonically active. Okay, so tectonically active region, if we made our structure along the principal stress direction, the stress will create the more and more damage towards our structure. So the stress measurement is very important for the mega civil structure if those structures laying in the high active regions. Okay, or so here are some methods. So based on these methods, we can measure the principal stress or stress directions. Borehole breakouts. Borehole breakouts is very common phenomena for the hydrocarbon exploration. So because in hydrocarbon exploration we drill up to 3 to 4 kilometers. So below 3 to 4 kilometers there is too many active stresses. So based on the sensors and based on the distortion of the borehole we can measure how much stress is acting on the boreholes. Then overcoring. Here in overcoring method, we drill one core at larger size that will be means a standard is 76 mm. Then we drill another borehole within that borehole that will be smaller than the outer one, that is 36 centimeter mm. So upper portion is made by 76 mm and the lower portion has dimension 36 mm. So we install the sensors there, and sensor detects the distortion in both the boreholes, and we compare the distortion and we calculate the stress direction in the boreholes. Then hydrofracturing. Hydrofracturing is the phenomena where we artificially we try to fill the rocks. So we try to fill the rocks means we want to measure the stress. So based on the hydrofracture testing in the rock, we calculate the principal stress direction and how much these rocks can bear. Then earthquake. So based on the earthquake distribution magnitude of the earthquake in particular regions, we calculate the principal stress direction, or we calculate or we take an idea which portion of the earth crust is more active than others. For an example, if we take an example from the Himalayan region, in Himalayan region most of the earthquake occurred along the MCT. So MCT is highly means MCT is that structure means central thrust is a highly active region in Himalaya, most active region, and the stress is also means more than other part of the Himalaya in the MCT regions. Then another method is active tectonics. If there is some active tectonic activity in any region, active tectonics means if we occurred the tectonic movements or block movements or any movement in the crust within 2 million years, 2 to 2 million years, 2 to 5 million years. So that activity comes under neotectonic activity. So based on the geomorphological indices like buried channels, triangular facets, tilted terrace, star terraces, unpaired terraces. So based on these regions or soft sedimentary structures those occurred due to seismic activity in the region, we can measure the stress in the region. So I hope you will enjoy this video. Thank you very much.